Last time, linear regression drew a straight line to predict a number, like the price of a house. But so many real questions aren't numbers at all. They're yes or no. Is this email spam? Is this transaction fraud? Is this tumor harmful? That's called classification, and it's one of the most useful jobs in all of machine learning. The simplest tool for it builds directly on what we just learned, and it's called logistic regression. Here's the setup. Say we're looking at tumors, and for each one, all we know is its size. The small ones turned out harmless. We'll call that class 0 down at the bottom. The larger ones were dangerous. Class 1 up at the top. And in the middle, around the medium sizes, things get fuzzy. Some go one way, some the other. Given a brand new size, we want to predict which group it belongs to. Now you might ask, why not just fit a straight line like we did before? The trouble is, a line never stops. It dips below 0 on the left and climbs above 1 on the right, and a probability simply can't do that. And honestly, what would a prediction of 1.3 or minus 0.2 even mean? Nothing. A straight line just doesn't fit a yes or no answer. So, logistic regression does something clever. It bends that line into an S shape, a smooth curve that eases up from 0 to 1 and never once leaves that range. Far to the left, it sits near 0, almost certainly harmless. Far to the right, it sits near 1, almost certainly dangerous. And in between, it slides smoothly through every value. That curve is a probability. How likely this tumor is to be the dangerous kind. To turn that probability into an actual decision, we pick a threshold, usually 1/2. Anything above the halfway mark, we call class 1. Anything below it, class 0. That crossing point is what we call the decision boundary. And notice, right at the boundary, the model is genuinely unsure. It's basically a coin flip. Step a little to either side and it quickly grows confident. The equation is almost the same as before. We still compute w times x plus b. That's our familiar straight line hiding on the inside. But then we wrap it in the sigmoid function, which gently squashes any number, however big or small, into a probability between 0 and 1. That little squashing step is the whole trick. It's the one thing separating logistic regression from the plain line we started with. The model simply learns the lo and b that make the curve line up with the data. In Scikit-Learn, the pieces are familiar. Logistic regression for the model, fit to train it, predict for the class, predict proba for the probability behind that class, and accuracy together with a confusion matrix to check how it did. Same rhythm as before. Let's go write it. Here's the whole program. It's a little longer this time, so we'll spread it across 2 short pages. But as always, nothing is hidden from you. Let's start with the first page, where we set everything up. The imports are nearly the same as last episode, with just 2 changes. We bring in logistic regression instead of linear regression, and from metrics we grab accuracy score and confusion matrix, because we're judging classes now, not numbers. So R2 score wouldn't make sense here. Then we build some data to play with. 60 small tumors centered around size 3, labeled 0, and 60 larger ones around size 7, labeled 1. We stack them together so that X is the size and Y is the class. That reshape at the end just tells Scikit-Learn that each sample has a single feature. We split it exactly like last time, 80% to train on, 20% held back to test, and a fixed random state so the split is identical on every run. That's the whole first page, setup and splitting. Now let's flip over to page 2, where the model actually does its work. Now we create the logistic regression model and we call fit on the training data. It is the same 2 lines as linear regression, and behind the scenes it's searching for the W and B that make that S-curve fit our 2 groups as closely as it can. Then we predict on the test set. Predict gives the class 0 or 1, while predict proba hands back the raw probability sitting behind it. Accuracy tells us the fraction we got right, here about 96%. And the confusion matrix lays it out in a little grid. 12 correct, 0 wrong on one side, just a single mistake on the other. The fastest way to see where it slips. Finally, we draw the picture. The points sit down at 0 and up at 1, and we plot the model's probability curve in red. That smooth S sweeping from harmless all the way up to dangerous. And you can see the decision boundary right there, where the curve crosses 1/2. And that's logistic regression, the very same shape of code as before, just predicting a category instead of a number. A line, then a sigmoid, then a probability. Next time, we'll meet a model that makes predictions with no equation at all. It just looks at the closest examples, that's k nearest neighbors,